Hello, I am Elias Johnson. I'm a graduate student at the Massachusetts Institute of Technology in the Department of Aeronautics and Astronautics. And today I'm happy to present an overview of a hazard analysis that was performed for the human supervisory control of multiple UAS systems. Just as a brief overview, there's a paradigm shift that's occurring in the control of UAS systems. In the past, multiple operators were responsible for providing direct control over a single UAS. And the operators provided direct control inputs to the flight, navigations, and payloads of a single system. However, in future operations, it's expected that one operator will be responsible for supervising multiple UAS. And the big difference here is that there's an autonomous controller that assumes some of the low-level control responsibility previously allocated to operators. In many of these applications, the autonomous controller helps develop plans for all of the UAS to work together to achieve the mission as a collective whole. And the operator provides inputs so the system can do this. And then it reviews all of the plans developed by the autonomous controller and can approve or deny these plans and ensure that the mission is completed effectively. So this really is a big paradigm shift, both in the control complexity and in the operational complexity of these systems. And so future multi-UAS systems require a rigorous early safety design process to inform the design requirements. And the objective of this research was to perform a hazard analysis and provide early design recommendations for these systems, and at a larger view, demonstrate how a process by which further design recommendations could be generated. Before I get into the results of the hazard analysis and the research presented for this research, I just wanted to provide a justification of why SDPA was chosen for this hazard analysis. And the challenge is that traditional hazard analysis techniques focus on component failures. But the problem is that this omits accidents caused by non-component failures and unsafe interactions that occur among system components. And future multi-UAS systems will have complex interactions between operators and autonomous controllers that may not be adequately captured by traditional hazard analysis techniques. And so a different approach is required. And for this research, that was systems theoretic process analysis. And systems theoretic process analysis takes a different view of safety, and it treats safety as a dynamic control problem instead of a failure prevention problem. And in SDPA, accidents occur because of unsafe interactions that are not properly enforced in the system. And the system is modeled as a feedback control loop shown on the left, and hazard analysis is performed on the interactions between the components. And this can be used to understand interactions between humans and automation, humans and humans, and others as well. And so there are 4 steps to SDPA that are going to be presented in this presentation, and that I'm going to walk through. The first step that we performed for this research was and the first step of SDPA is to define the purpose of the analysis. And for SDPA, that's losses. And losses are just unacceptable things that cannot happen during the design and operations of the system. These losses for this analysis included loss of mission, loss of life or permanent disabling injury, and loss or damage to the UAS equipment. From there, hazards are developed, and hazards are ways that the losses could occur in a worst-case environment. And they are documented here. And the rest of the analysis is focused on understanding how these hazards could occur during the design and the operations of the system. So the next step is develop the control structure of the system that's going to be analyzed. And abstraction can be used in SDPA to manage these future multi-UAS systems. And for this, you can see at the top, there's an operator in command who provides a mission intent. And this mission intent could be consider a number of different parameters. This could be For UAS system could be no-fly zones. This could be a list of targets that or a list of tasks that need to be accomplished. But here it's be kept at a very abstract level so that the analysis is applicable to a wide range of multi-UAS applications. So once the operator provides the mission intent, the multi-UAS fleet controller develops the plans for the UAS team, and it provides the feedback on the proposed courses of actions to the operator in command, and the operator can either approve or deny these courses of action. And these are the control actions that the operator provides to the multi-UAS fleet controller. Once the multi-UAS fleet controller receives the approved commands, they send out the mission tasks to the UAS to accomplish the mission. The important notice here is that this isn't a task that just happens once. This is something that happens potentially several times or multiple times throughout the mission. The next step of SDPA is to understand how the interactions among the components that have been developed in this model could lead to the hazards and ultimately the losses. And that is done by the identification of unsafe control actions. And an unsafe control action is a control action that in a particular context or worst case environment will lead to a hazard. And there are 4 ways that a control action could lead to a hazard. Not providing the control action leads to a hazard. Providing the control action leads to a hazard. Providing a potentially safe control action but too late, too early in the wrong order leads to a hazard. Or providing a control action that lasts too long or stopped too soon leads to a hazard. And what we're going to do for this presentation is just look at one control action and one way that a control action could lead to a hazard that was generated in the entire analysis as a demonstration. And so we're going to look at how the operator approving or denying a course of action could lead to a hazardous system state. And one of the ways that this could occur is by providing a potentially safe control action, but too late. And the specific context of when this providing it too late, shown by the UCA below, is that the operator provides approved course of action too late when there is a time critical or time sensitive task that must be approved and executed. So now that we've determined the unsafe control action, the next step of SDPA that was done for this analysis was to determine why might the operator provide an approved course of action too late. And that is done through SDPA in the generation of causal loss scenarios. And the causal loss scenarios describe the factors that lead to the unsafe control action and hazardous system state. And so we're going to go through one example that was generated in the analysis here. So for instance, let's say that the mission that the UAS is accomplishing is a reconnaissance mission. And the operator has provided some previous mission intent on potential targets to investigate. And the multi-UAS fleet controller determines that they need to interrogate a stationary target. And so it develops plans for this for the team of UAS. And those requests are sent to, or those plans are sent to the operator in command. But there's a movement of the target. And the stationary target is no longer stationary, and it's going to be out of range in 2 minutes. But this was not communicated to the operator. So they believe that the task is not time critical. And so they attend a time critical task first, and they eventually approve it. But by the time that it's approved, the task is executed too late, and it's no longer relevant, or the target, or it's no longer achievable because the target is out of range. So this is just one example of how we can develop a causal loss scenario that's caused by a breakdown in the feedback control structure. And this can be, and this leads straight to the hazard where the UAS does not complete the mission objectives and tasks. And this can be formally documented with traceability that was performed throughout the analysis. From here, we have the operator in command may provide a confirmed action too late because a task that was not originally time sensitive when requested by the UAS fleet controller becomes time sensitive because of changes in the environment. And we looked at movement of the target, and there was no feedback to alert the operator in command. So from this causal loss scenario, we can generate systematically generate safety-driven design requirements for the future multi-UAS systems. And one of these requirements that was generated in the analysis is there must be a feedback mechanism to alert the operator when a non-time sensitive task becomes time sensitive. And these requirements and the causal loss scenarios also lead to additional questions that may need to be addressed with additional human factors research or additional hazard analysis. And so it can become an iterative process where we make recommendations for the system and trade studies are performed for the additional recommendations that are created. And so one question that might need a trade study is, how should the operator be alerted when a task becomes time critical? And another one is, how should the feedback for non-time critical tasks differ from time critical tasks? Another potential design requirement is that the multi-UAS fleet controller must have a means to update or delete requests if it determines the action is no longer consistent with the mission objectives. And from here, we can see that there is direct traceability from the design recommendations back to the causal loss scenarios. And so this was just one example that was provided in the full analysis. In the complete analysis, there were 130 causal loss scenarios related to human supervisory control. And overall, it demonstrated a process for developing design requirements early in multi-UAS systems. And that is everything for this presentation, for this overview. Here are the references. And that's the end of the presentation. Please feel free to contact the team with any questions, and I can be reached at the email address there. Please read more about our paper, and I'm looking forward to receiving any questions. Thank you for your time.